In previous videos, I've talked about having additional information, and that is information in the form of, say, y of x naught is equal to y naught. It's called an initial condition. It's a point on the solution curve. And a differential equation together with an initial condition is called an initial value problem, an example of which we have here. The equation is quantity 2y minus 2 dy dx is equal to 3x squared plus 4x plus 2. You'll find this is easily separable. We're asked to find an explicit solution, and that means we need to isolate y. You'll find the integration is pretty straightforward, uses the power rule. Little tricky to solve for y, but go ahead and do that. See if you can apply the initial condition. It's y1 equals negative 2, and it just really means when x equals 1, y equals negative 2. And then come back, see how you did. I didn't get very far, but I wanted you to see how I handle some nuances here. After separating by multiplying both sides by dx and then integrating using the power rule, we have y squared minus 2y equals x cubed plus 2x squared plus 2x plus c. First thing, I want to solve for y, and here we're going to actually complete the square. And since we have y squared minus 2y, we cut that linear term in half, square it, and in this case we're going to add 1 to both sides. Left-hand side factors into y minus 1 quantity squared. Right-hand side remains unchanged after adding 1. Now I'll use the initial condition. When x is equal to 1, y is equal to negative 2. Making those substitutions is going to give us that c is equal to 3. Turning our equation into y minus 1, the quantity squared, is equal to x cubed plus 2x squared plus 2x plus 4. In order to isolate y, we are going to square root both sides, giving us y minus 1 equals plus or minus square root of what had been the right-hand side. And then finally y equals 1 plus or minus the square root of x cubed plus 2x squared plus 2x plus 4. Now, we have this plus or minus here, and that's kind of problematic because it's two different solutions. But if we look at our initial condition, y of 1 equals negative 2 means y is negative. If I have y equals 1 plus a square root, that's never going to be negative. And so the initial condition requires us to have that minus there. So the explicit solution is y is equal to 1 minus the square root of x cubed plus 2x squared plus 2x plus 4. Now, as far as an interval of solution, we need values of x that will make the radicand non-negative. But additionally, we have to remember that this is going to go in, it came from an equation, or checking it, we'll say, would go into an equation where we have a dy dx. So for y prime, we'd have that radical in the denominator. So ultimately, what we need is that x cubed plus 2x squared plus 2x plus 4 is greater than 0. I encourage you simply to differentiate this function y to convince yourself why we have a strict inequality. This is factored by grouping, and we're going to find x squared plus 2 times the quantity of x plus 2 is greater than 0. X squared plus 2 doesn't contribute to the expression being positive or negative, and so the interval of solution is going to be from parenthesis negative 2 to infinity. Now we were asked to graph it, which I've done here. You can see I've got y equals 1 minus the square root of blah, 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 blah. This, by the way, was done using GeoGebra 2D. And here we have the curve, which starts at negative 2. We said that was the interval of solution. And we also see the point 1, negative 2 is on the curve. That's the point associated with the initial condition. And it should always be the case that if we have an initial condition and can graph a function, the initial condition point needs to be on the curve. Otherwise, something went wrong. Now we might wonder, if I have a solution curve that goes through a point, is there another one that would also solve the differential equation and go through that point? And turns out the answer is no. Given an initial value problem, dy dx equals a function of x and y subject to an initial condition y of x naught equals y naught. Given a rectangular region in the xy plane, that contains the initial condition point if the expression on the right-hand side, f of xy, is continuous, and its derivative with respect to y is also continuous, then there exists an interval inside the region and a unique function that solves the initial value problem. All that really says is, if we have an initial condition point and can identify a neighborhood around it where both the function and its derivative with respect to y that defines the expression on the right-hand side of the differential equation is continuous, then there's only one solution that goes through that point. Now, I don't want you to spend too much time thinking about that, but it's the thing I need to tell you. That was for first order differential equations, and then higher order differential equations will come later in the course. For now, let's go back to solving a separable differential equation. Here we're looking for an explicit solution, so y should be isolated. The initial value problem is dy dx is equal to y squared times the sine of x squared with an initial condition y of 2 is equal to, y of negative 2 is equal to 1/3. Now we're first going to separate. So we have y to the negative 2 dy is equal to the sine of x squared dx. Ordinarily, we would integrate both sides. And on the left-hand side, it's not a big deal. We have negative 1 over y. But on the right-hand side, we can't integrate that. So what we're instead going to do is we're going to turn both of these integrals into definite integrals. So I'm going to write the integral on the left-hand side as the integral from, of y to the negative 2 dy from, now here's an interesting thing, we're going to use the initial condition input value, in this case, negative 2. And then we're going to make the upper limit of integration x, and we'll see how that works out. We want it to be the same type of integral on the right-hand side, so it also is going to go from negative 2 to x. Then we have our sine of, well, I can't write down sine of x squared if the upper limit of integration is x. And so what we do is we use a dummy variable. I have sine of t squared dt. If we were able to anti-differentiate the right-hand side, we would substitute the t's using x and negative 2 according to the fundamental theorem of calculus, and the t's would be gone and it's a function of x. Now on the left-hand side, we have negative 1 over y evaluated from negative 2 to x. Now here's where things get a little bit weird. We integrated on the right-hand side with respect to t. On the left-hand side, we integrated with respect to y, but y is a function of x, and x is temporarily being replaced by t. And so to help understand what's going on, I'm going to write this down as y of t in the denominator on the left-hand side. Right-hand side remains unchanged because we can't do anything with that integral. Now on the left-hand side, we have negative 1 over y of t evaluated from negative 2 to x, and then again, using that fundamental theorem of calculus, I'm going to write it down as negative 1 over y of x minus, so plus 1 over y of negative 2. Right-hand side again remains unchanged. Now I don't know what y of x is, but that's okay, that's what we're solving for. We do happen to know what y of negative 2 is. That's why we used the initial condition value as the lower limit of integration. Y of negative 2 is 1/3, therefore its reciprocal is going to be 3. And the right-hand side remains unchanged. At this point, we want an explicit solution. We're going to solve for y by subtracting 3 from both sides, but then multiplying by negative 1, and then finding the reciprocal. The result is going to be y of x is equal to, I'm going to write it as 3 minus that integral from negative 2 to x of the sine of t squared dt. Then I'm going to wrap the whole thing in parentheses, make negative 1 the exponent. So that's how we're reciprocaling the right-hand side. We don't have to write down a fraction that has an integral in it.